Hey guys, it's Mr. Roach again, coming for you guys Tuesday lesson, March 24th, 2020. Uh, just to recap of what we learned from Monday, from yesterday. We're starting to focus on that force and motion of this unit, reminding that the force is a push and a pull, that the two main forces that we're going to focus on inside of the force and motion unit will be friction, which basically opposes the motion in which you want to go. We can think about friction when we rub our hands together. We're trying to get that heat and we're trying to get that warmth, but as you go up and you go down, that's where the friction is really coming in. You move your hand up, the other direction is going down, and you can feel that friction, which then causes that heat. Gravity is something that we see all the time when we throw the ball up in the air, whether it's a football, a baseball, even a soccer ball that goes up. The ball eventually does go up, but in the end, the ball does come back down to the center of the earth. A couple more things that we got to remember about gravity is that the further the distance it is, so when we talked about it yesterday, we drew that picture that if you're on Earth, Earth is so big that the gravitational pull doesn't really affect us, that we don't feel it, and that we stay to the center of the Earth. But the further we get out into space and away from Earth's gravity, we lose the effect of Earth's gravitational pull, and then we weigh less and we can float like the astronauts do in space. The bigger the mass, the more gravitation it has. Hence why the moon circles around the Earth because the moon is bigger. The Earth is bigger than the moon, and while we circle around the sun because the Earth is smaller than the sun. Today, we keep on going on learning about different things about friction. So let's go ahead and read our I can statement. I can understand and explain how the factors such as force, gravity, friction, and other effects motion. Looking at our bell work for today. Jose fills a glass container completely with water and screws the lid on tightly. He places the container in a freezer, which will most likely result. Would it be A, the container will prevent the water from freezing? B, the water will freeze and take up less space in the container? C, the water in the container will expand when it freezes and causes the container to crack? Or D, the container will absorb heat from the water, causing it to crack? Okay. First things first, as we always, we teach you guys, make sure you read the question again for understanding, and then read the answer choices to figure out which answer best would suit the answer that goes with it, because you're looking for the one that most likely will result. So just breaking it down, looking at A, the container will prevent the water from freezing. Okay. That's not going to happen. It is a glass container, so the water inside the glass container, if we've ever put anything in our freezer, we know that anything is going to freeze. Regardless, the container won't prevent the object from freezing. The object is going to freeze. So it can't be A. B, the water will freeze and take up less space in the container. Okay, so we know that the water will freeze, but will it take up less space? Hmm. Could be. We're going to save that one, but we're not quite sure. C, the watering container will expand when it freezes and causes the container to crack. Okay, so we do know the water will expand. We do know it's going to freeze, um, but cause the container to crack. We'll see. The container will absorb the heat from the water, causing it to crack. Not very likely. The container is not going to absorb the heat. Um, so we're going to say D's out as well. So we end up with B and C. But we know that when we have a substance, especially going from a solid, a liquid, and a gas, that it's a state of matter change. So regardless, the mass is going to still stay the same, right? Because mass cannot be created nor destroyed, so the mass is going to stay the same. So B says the water will freeze and take up less space. So if the water originally started with 32 grams, when we freeze it, it's still going to be 32 grams. It's not going to shrink. It's not going to take up less space. It's going to stay the exactly same. It's just going from a liquid to a solid state. All right. So it will still take up the same amount of space. So B is not really the answer. It's going to take up the same amount of space. It's just going to freeze. When it freezes, it is going to expand out. It's going to get bigger because the water molecules are stretching out, and it might cause the container to crack. All right, because if it keeps expanding out, and it needs to take up more space, then if it's in a confined container, it might crack the container. It might not break, but it might definitely crack the container. So our right answer would be C. The water in the container will expand when freezes and causes the container to crack, right? Moving on to our next slide. All right, today we want to talk about weight. Okay, so yesterday we talked about gravity and friction, mainly focused on this gravity part. Uh, Whenever we think about gravity, we cannot think of gravity, weight, and mass being the exact same thing because they are not. They're not interchangeable. You can't say weight and mass are the same because they completely are totally different. Weight is the resulting gravity pushing down on an object. So whenever we do get on a scale, you put your baby sister, your mom checking your weight, you go to the doctor and they tell you step on the scale. We get our weight from knowing the amount of gravity pressing down on you. So how much gravity is being pulled on that object. So that's how we get our weight. Um, when we talk about mass, it's saying how much stuff is in that object. So when we talk about a bowling ball, how much molecules, how many atoms, how much material went into making that object. That's mass, how much stuff is in that object. Those two terms are not interchangeable. They are not the same. We're going to explain why. So when we're thinking about weight, and we're saying that weight is almost dependent on gravity, how much gravity is being pressed down on you, and we know that gravity might not be the same from A to B. Because we know on Earth, when we jump, we come back to the center of the Earth. Because we know that Earth gravity is strong. But we do know our astronauts in space, when they go to the moon, they can float. Why is that? Take some time. Think about that. Okay, so we talked about it yesterday. We said that the moon is smaller than the earth. So we know that the moon is smaller than the earth. That means the moon must have less gravitational pull. Less gravitational pull means you weigh less on that object. So again, the more gravity you have, the more you will weigh. The less gravity you have, the less weight you will have. So again, the moon is smaller than the earth. So when we go, or whenever someone goes to the moon, they weigh less. Hence, that's why they can jump and float inside of space because they weigh less. It's less gravity pulling on them. What I want you guys to think about, what I want you guys to think about when we're thinking about planets, all right, we have Earth and we have Jupiter. We have Earth and we have Jupiter. Would you weigh more on Jupiter or would you weigh more on Earth? Jupiter, Earth, Jupiter, Earth, right? We should know, hopefully we do know, that Jupiter is bigger. Jupiter is one of the biggest planets in our solar system. So if Jupiter is a bigger planet and it has more mass, then it must have a bigger gravitational pull. Okay? So if it has more gravity, that means you're going to weigh more on Jupiter than you do on Earth. So you will weigh more on Jupiter than you do on Earth because Jupiter is a bigger planet. All right. However, let's change this up. The mass. All right. We do know weight and mass are not the same. All right. Wherever you go in the universe, your mass will always be the same. It will always be the same. All right. You can go on Pluto. You can go to Venus. You can go to Mars. Your mass will not change at all. So we're using Jupiter as our example again. Would you have the same mass on Jupiter as you do on Earth, or would it be different? Take some time to think about that. Your mass will be the exact same. All right. If you would go to Jupiter, if you would go to Neptune, if you guys would go to Mars, Venus, Saturn, your mass will still remain the same. It's still the amount of stuff that's in that object. All right. You're not being rearranged. Your body's not morphing. You're not turning to, if you're a human on Earth, you're not turning to a puddle of water on Jupiter. All right. You're still the same amount of stuff that you are on Earth that you will have on Jupiter. Okay. So mass will always be the same regardless of wherever you go. Your weight, however, can change depending on how big that object is, right? So remember that. All right. Again, another thing we're going to talk about today is balance and unbalanced forces. So when we're talking about that push and a pull, remember that gravity being a pull, that push being that uh, friction factor of our force and motion unit. We two things that we can describe if things are moving or things are not moving is that a balanced or unbalanced force is what we describe when objects are being upset. All right. So when objects are standing still, they're equal, they're balanced, then we call that a balanced force. There's no net move, there's no movement. So if we're looking around us and we see a pencil on our table and that pencil is standing exactly still, it's at rest, it's balanced. All right. The object motion did not change. It's staying at rest and it will remain at rest until something else comes in contact with it. Okay, so a balanced force will be when an object is completely at rest, when it's not moving. All right, the object staying the same and it will remain the same. If we're looking at our PowerPoint, we notice that we see on the right and on the left, we see 5N. That N stands for net force. All right, so if we're going to the left and the net force is 5, and to the right that the net force is 5, it's saying that that net force is completely balanced. From the left and to the right, it's a balanced force. So it's not going to move. Balanced force. An unbalanced force is when something pushes it, when another object comes into unequally and pushes that object. So going back to the pencil example that we have. So your pencil's on your desk. A huge gust of wind comes in through the window and the pencil moves. What was the force that acted upon the pencil to make it move? It was the wind. The wind made the pencil move. It's no longer balanced. It moved. It didn't stay at rest. So, an unbalanced force is when an object moves, its motion would change, either its speed, its direction, or the position. So, the wind acted as the force, came in and moved the direction of the pencil. It changed the speed of the pencil and the position. It's no longer standing still. All right, if we notice on the screen, it says the net force is 5 to the left. There's no other net force to the right. That means there is an unbalanced force, that something's trying to move it. Another common way that we can think about balance and unbalanced force is tug of war. All right, we all love tug of war when we get the opportunity to play it. All right, so if we have 5 players to the right and 3 players to the left, it doesn't seem like that would be balanced. We have 5 players to the right, we have 3 players to the left. That's not a balanced force. So in all honesty, the 5-player team is going to win because they have more force on their side. The 3-player team will lose because they have less force on their side. But I'm a fair teacher, so are the rest of our teachers. We want it to be balanced. We want it to be super even as always. So we're going to put 5 on the right. We're going to put 5 to the left. You guys tell me, is that a balanced force or an unbalanced force? It's a balanced force, guys. We have 5 to the right, 5 to the left. If we're going to say that they have the same amount of strength, then it will be a balanced force. It will be no change in direction, speed, or position. So that's a balanced force. Okay? That's all we have for today, guys. All right, so after you get done watching this video, make sure you guys go to Discovery Ed and do your assignments for today. Make sure you're doing everything inside Discovery Ed, engage and explore, doing all the activities inside of the reading or activity. As soon as you get done with your Discovery Ed question, please make sure you head back to Google Classrooms to figure out that exit ticket. Again, all of this is to ensure that we know you're doing your work. You guys can get credit for your e-learning activities. We definitely want you guys to still maintain that knowledge during this e-learning break. But make sure you guys are doing all the activities inside Discovery Ed and along with the exit ticket so we can give you credit for the day. All right, you guys, we see you tomorrow. Be prepared to learn some more.